Now what we did in class, we cranked the circuit as you saw before with everything connected, and then we just disconnected the generator. This is the generator. We just took the generator away and left the capacitor sitting there in a series circuit with the resistance and the coil. So we have a current flowing through the resistance from the capacitor, because the capacitor stores positive charge on one plate, negative charge on the other. The positive charge wants to join up with the negative charge. The only way it's got to do that is for the positive charge to travel around this way, or the negative charge to travel around this way. It doesn't really matter which goes where. It's equivalent to positive charge moving in this direction. And our convention is that current flows in the direction that positive charge would go. Even though after this convention was devised, we learned that it was electrons that are actually flowing in this direction. We made an arbitrary choice early that positive charge flowed toward negative, and we kept that convention. And in some cases, of course, that's exactly what happens. In some kinds of ions, in some kind of electrolysis and electroplating, that's what we have. Now, the capacitance here is the charge divided by the voltage. That's how we define capacitance. So it follows that the voltage across this capacitor is the charge divided by the capacitance. Just solving this equation, or this definition for the voltage. Okay, capacitance being charge to voltage ratio. A large capacitance stores a lot of charge for small voltage. That's often a desirable quality. Okay, it follows that voltage is charge over this capacitance that we defined here. What happens now? We're going to actually write a differential equation and invoke a little bit of calculus to solve it. That's going to be way beyond the scope of Principles of Physics and a Physics 121 course, and somewhat beyond the scope of even the Physics 201, although there's only one step that a 201 student wouldn't understand. Okay? Now the idea is that this voltage, which is charge over capacitance, creates a current. Of course, the current is just voltage divided by resistance. So that whatever the voltage is here determines what the current's going to be. When the voltage is higher, you're going to have more current. Now, the key thing to understand here is the current is the rate at which charge flows from plate to plate. So that the rate at which the charge is changing is just the current. Okay? If we have a current of 1 coulomb per second, that means charge is being neutralized in this capacitor at the rate of 1 coulomb per second. And when the charge changes, the voltage changes. If the charge decreases, the voltage decreases. If the voltage decreases, the current decreases and carries the charge away less quickly. Now let's get a mathematical handle on that. What we said is that the current is voltage divided by resistance. The voltage is just Q over C, so we divide Q over C by the resistance and we get Q over RC. That's our current. But what's current? It's the rate at which charge passes a given point. And in this case, that's the rate at which charge changes on the capacitor. So it's delta Q over delta T. That approaches a limit that we call dQ over dt. Now, in the limit, as delta T, as the time interval gets very short, we approach this dQ dt, which is what we get in the limit as the time interval approaches 0. University physics students will understand this, college physics students will understand this, and principles of physics students should understand this delta Q over delta T idea also. From here on, it gets maybe just a little mysterious for anybody but the university physics students. But since, remember, I is the same as Q over RC, and I is dQ over dt, we can certainly write dQ over dt equals the Q over RC. Now we get into a little trouble with signs here. Actually, the current up here should have been negative Q over RC. in the direction that we're going. But we're just going to take care of that here by waving our hands a little bit. We can be rigorous with that, but you can read about that if it's important to you, as it is if you're a university physics student. But the whole idea is simple. The charge is decreasing, so the rate of change of the charge should be negative. So this comes out negative Q over RC, and there's the differential equation. Okay? And this just says that the rate of change of the charge, dQ over dt, is equal to negative Q over RC. Now, we do a little bit of algebra here. We get all our Q's on one side. Our dQ is here, and our Q is here. And then we put the dT's and any T's that we might have on this side. We get this equation. Now calculus students will verify that it's easy to solve this equation in this form by simply integrating both sides of the equation. You do this calculus operation called integration, and you see that this thing, when integrated, gives you natural log of Q. When integrated, this just gives you negative T over RC, and you have this thing called an integration constant that we'll add on just one side here. We get integration constants on both sides, but we just lump them together into one constant. Then we take, and now Physics 201, general college physics students can follow this. We simply take, we exponentiate both sides. That is, we do e to the natural log of Q to get Q, and e to the negative T over RC plus constant to get e to the negative T over RC plus constant. And that's just e to the constant times e to the T over RC. E to the constant is itself a constant, and it has to be greater than 0, whether the constant is positive or negative. This is still positive. And we end up with Q equals C e to the negative T over RC. And this is a function that describes how the charge on this capacitor will change as that charge discharges through the resistor, carrying a current through the coil as it happens, as it discharges. So there's the function. Q equals C e to the negative T over RC, and we're going to analyze what happens and what we observe in terms of this function in just a minute.